In this question, we have a beryllium-9 nucleus, which has an exact mass of 9.012183 U per nucleus. U is a unit called the atomic mass unit, and it represents really small values of mass. Our first step is completing the table with the numbers and total masses of the protons and neutrons in beryllium-9. So looking at our nuclear symbol here, we have an atomic number of 4 and a mass number of 9. So an atomic number of 4, that means we have 4 protons. A mass number of 9 means we have 9 protons and neutrons together. So 9 protons and neutrons minus 4 protons gets us 5 neutrons. So we can go ahead and fill that in. 4 protons and 5 neutrons. Now we need to figure out the expected mass of those protons and neutrons. So looking over here at this table, we can see that a proton has a mass of 1.007276 U, and a neutron has a mass of 1.008664 U. So for the expected mass of protons in the nucleus, we know we've got 4 protons, and we know that the mass of a proton is 1.007276 U. So if we multiply those together, we get 4.029104 U for our mass of protons. And for neutrons, we've got 5 of them, and we know from the table that the mass of a neutron is 1.008664. So if we calculate that out, we're going to get a total mass of 5.043320 U. So we can go ahead and fill that into our table. Next, we have to find our expected mass of beryllium-9. So the expected mass is just going to be the sum of the masses of all the protons and neutrons. So we're going to go ahead and add those together. So we had 4.029104 for our mass of protons, plus we had 5.043320 for our mass of neutrons. Adding those together gets us a total expected mass of 9.072424 U atomic mass units. So we can go ahead and fill that in here. So if we compare the exact mass given in the question, which was 9.012183, with the expected mass, we can see that our expected mass is greater than our exact mass. The reason why is that when protons and neutrons form a nucleus, they become tightly bound and energy is released. And energy and mass are actually equivalent. So if we release energy, that means that the measured mass is going to be less than we would expect it to be based on all the parts. So the mass defect, that's the difference between the expected mass based on all the parts added up and the actual mass, which is slightly less. And to calculate the mass defect, all we need to do is subtract the actual mass from the expected mass. So our expected mass was 9.072424 minus our actual mass, which was, from the question, 9.012183. So if we go ahead and put that on our calculator, we're going to get a mass defect of 0.060241. And the units for that are U per nucleus. And that was actually the same for our expected mass. So U, that's our atomic mass units, and it's per nucleus because we're talking about just in one nucleus. So let's go ahead and fill that in. We've got 0.060241 U per nucleus. That's the difference between our expected mass and our exact mass. So that much mass was released in the form of energy when our nucleus formed. Now we're going to need to calculate the nuclear binding energy. In order to do that, we're going to need our mass defect in units of kilograms per nucleus. So we're going to have to do a conversion here. Let's clear up some space. So we're starting with 0.060241 U per nucleus. And we need to convert into kilograms per nucleus. Let's head to the reference sheet. Here we can see that an atomic mass unit is equal to 1.6606 times 10 to the negative 27 kilograms. So 1 atomic mass unit is equal to 1.6606 times 10 to the negative 27 kilograms. That's our conversion factor we're going to use in this conversion. So I can set up my conversion table. Right now I have U on top, but I want that to change from U per nucleus to kilograms per nucleus. So I'm going to put U on the bottom so that that will cancel out. And I'm going to put kilograms on the top because that's what I want to end up with. So I can see from my conversion factor, I've got 1 U is equal to 1.6606 times 10 to the negative 27 kilograms. So I can go ahead and cancel out the U on the bottom and the top. And that leaves me with 0.060241 multiplied by 1.6606 times 10 to the power of negative 27 divided by 1. Putting that all on my calculator, I get an answer of 1.00 times 10 to the power of negative 28 kilograms per nucleus. So we can go ahead and enter that number in our answer box here. Remember, times 10 to the power of is written as E when entering numbers on this platform. Negative 28. So 1.00 E negative 28. Awesome. So we've converted our mass defect from atomic mass units per nucleus into kilograms per nucleus. Now we can use them in the equation for the nuclear binding energy. Just as when the neutrons and protons came together to form the nucleus, energy was released, we need to add energy to our nucleus in order to break it apart. So that is called the nuclear binding energy, the energy required to separate the protons and neutrons in a nucleus. Here's our equation for binding energy. It's E equals mc squared, where E is the binding energy, m is the mass defect, and c is the speed of light. Now, we're told here mass defect needs to be in kilograms per nucleus, and c is in meters per second. That gives us a binding energy in joules per nucleus. So we've got E equals mc squared. So m, that's our mass defect in kilograms per nucleus, which we calculated as 1.00 times 10 to the power of negative 28. Then it's multiplied by c, which is the speed of light. Here we can see the speed of light is 3.00 times 10 to the power of 8 meters per second. 3.00 times 10 to the power of 8. And that is squared. So if we put that all on our calculator, we're going to get out a binding energy of 8.99 times 10 to the power of negative 12. And our units there are joules per nucleus. So again, we can go ahead and enter that in the answer box. we've got 8.99 times 10 to the power of, remember that's E on this platform, negative 12 joules per nucleus. Awesome. So we figured out our binding energy for one nucleus in units of joules. However, our final step is to figure out the nuclear binding energy for a whole mole of beryllium-9 nuclei in units of kilojoules per mole. So we're going to have to do another conversion. So we're starting with 8.99 times 10 to the minus 12 joules per nucleus. Our first step will be to convert joules into kilojoules. Now, kilo means 1,000, so 1 kilojoule is the same as 1,000 joules. So that's our conversion factor we're going to be using here. I want joules on the bottom so it will cancel out. And I want kilojoules on the top because that's what we want to end up with. We've got 1,000 joules then on the bottom and 1 kilojoule on the top. That will do our joules to kilojoules conversion. Finally, we need to do the nucleus to mole conversion. Here on our reference sheet, we're given Avogadro's constant, which tells us the number of particles in 1 mole. 1 mole has 6.02 times 10 to the power of 23 particles. Or in other words, 1 mole of nuclei has 6.02 times 10 to the power of 23 nuclei in it. So 1 mole of nuclei is equal to 6.02 times 10 to the power of 23 nuclei. That is going to be our conversion factor for the second step in our conversion. So right now we have nucleus on the bottom of our fraction. We want to get rid of that. So I'm going to put nuclei on the top. And we want to convert into moles. So I'm going to put moles on the bottom. Then we can add from our conversion factor that 1 mole on the bottom is equal to 6.02 times 10 to the power of 23 nuclei on the top. Then the joules will cancel top and bottom. The nucleus and the nuclei will cancel. And we're left with 8.99 times 10 to the power of negative 12 multiplied by 1 multiplied by 6.02 times 10 to the power of 23 divided by 1,000 times 1. If we put that all in our calculator, we end up with a number of 5.41 times 10 to the power of 9. And our units we're left with are kilojoules on the top and moles on the bottom. So kilojoules per mole. So we can go ahead and fill that in our answer box. Times 10 to the power of is E. So 5.41 E9. So we started off with the nuclear symbol for beryllium. And from that, we figured out firstly the expected mass. Then we calculate the mass defect. We converted that into kilograms per nucleus. And we used that in E equals mc squared to figure out the binding energy of beryllium-9, which finally we converted into kilojoules per mole.